So hello guys, here we have question number 16 from Build Up Your Understanding exercise of the chapter Oscillation and Waves. So let's look at the question first. A block of mass m can slide without friction on horizontal frictionless floor. A small block of mass small m is suspended by a light inextensible cord of length L from the hanger fixed on the top of the vertical pole, rigidly mounted on the block so that the ball can swing freely in the vertical plane. When the block is held fixed, the time period of small amplitude oscillations of the simple pendulum consisting of the ball and the thread is t0. What would be the period of small amplitude oscillations of the simple pendulum if the block were not held fixed? So if you want to try it without the hint, you should do it now. So if you want a hint, here it is. Actually, it is the same as that in the answers, so you can check it out also once. That for small amplitude oscillations, the ball can be assumed moving almost horizontally without an appreciable loss in accuracy. So if you want to again try it with the hint, you should please do it now. So now let's look at the solution. So first of all, let's consider in the case when m is held at rest. So here it is simply a case of a simple pendulum with the time period of 2 pi root of L by G. So there is no much trouble in this case. This can be derived simply. Now let's consider the important case in this when m is also moving. So here we can approach this in many ways. Actually, we can approach this in the frame of m. We can even do it in the ground frame, or even more simpler is the COM frame. But I personally prefer the frame of mass capital M. So let's observe in that. So let's assume that the block is displaced by a distance of x from its vertical position, and the length of the thread is L, and the angular displacement is theta. So from here now, if we observe in the frame of capital M, first of all we need to find the acceleration of m, so that we can get the pseudo force on small m. So the acceleration of m will be a equals to t sine theta over m in the right direction. This can be seen from the tension on the pole, or indirectly on the mass will be in the right direction of t sine theta. So its acceleration would be t sine theta over m. So now in the frame of m, we have to apply a pseudo force ma in the left at that instant to consider its motion. So here it is the FBD of the small mass m, or the small ball m. So these are the forces on it, and this is its acceleration. So here I have used the fact that it is small amplitude and the displacement is only in x direction. So here that's why I have considered the acceleration only in x direction. So from here what we get is mg equals to t cos theta, first of all, by equilibrium in vertical direction, and as the theta is very small, t approximately equals mg, and t sine theta plus ma equals to ma1. So from here what we get is mg sine theta plus mg sine theta times m over m equals to ma. Here I have substituted t from the above equation. So from here what we get is mg sine theta times 1 plus m over m equals to ma1. So from here the acceleration a of the ball or the bead which is swinging is g by L times 1 minus 1 plus m over m times x, and here we got the acceleration as a function of displacement. So this is a simple harmonic motion, and this is a restoring force. So there's a negative sign here, but I have just considered the magnitudes here. So this quantity here I have marked, this will be equals to the omega square, where omega is the angular frequency. So from here the time period will be 2 pi by omega, and substituting the value of omega here, we get the time period t equals to 2 pi root L times m over g times small m plus capital M, and as a function of the time period in the original case, this we get time period of this in this case is t naught root of m over capital M plus small m. So that's the final answer. And one more alternate exists to this question, that using the Lagrangian method. But I personally do not like it very much, and it is also not very necessary for JEE advanced or for Olympiads to much extent. So if you still want to try it, you can go through the method on Wikipedia or through David Morin, and you can give it a try once yourself. If you still face some troubles, you can ask me in the comment section. So that's the final answer. Thank you guys. Bye.